But then he took a pair of parallel plates, metal plates, above and below this luminous beam, and he put a potential difference on them, some delta V, and this delta V is just a fraction of what this delta V is. Okay, so it's very small. But what he noticed is that some of this luminous beam was actually attracted toward that positively charged plate. All right? And so, if you've got something that's attracted to this positively charged plate, what does it mean about this particle? It's negatively charged. Yeah, it's just Coulomb's interaction. And he could measure, right here, the amount of deflection from the center line. I'm going to call that amount of deflection delta x sub minus to indicate that this looks like a negatively charged particle. Now, Thomson also knew enough electromagnetism at that time to realize that the amount of that deflection has to be directly proportional to the charge on that particle. In other words, the greater the charge, the larger the deflection. So I'm going to represent that charge by E sub minus. He also recognized that the heavier that particle, the more difficult it's going to be to deflect this particle, or to deflect the particle to the positively charged plate. So that amount of deflection is going to be inversely proportional to the mass of that negatively charged particle. All right, but then Thomson did a further experiment. He increased delta V even more. And here I'm taking a little liberty with the story. It's a little bit more complicated, but I'm just trying to get the essence here across. And he cranked this up some more. And then, if you looked really, really carefully, what happened is he also saw some of this beam deflect toward the negatively charged plate, indicating that, lo and behold, there must also be some positively charged particles in this luminous beam. And he called that deflection delta x sub plus. All right? So delta x sub plus. And again, the amount of deflection for the positively charged particles has to be proportional to the charge on that positively charged particle and inversely proportional to the mass of that positively charged particle. All right, but the other critical observation that he made is that the amount of deflection for a given voltage, the amount of deflection for that negatively charged particle was much, much, much larger than the amount of deflection for the positively charged particle. So that's the evidence. And now we have to think. Now we have to make some guesses. And what he guessed is that the positively charged particles here, he guessed that these were H plus. How did he know that? Well, what he did know is that in this plasma, there were some hydrogen atoms, neutral hydrogen atoms. He knew that. How he knew that, I'm going to tell you, or we're going to talk about in a few days. But he knew that this plasma takes the H2 molecule and tears it apart, makes hydrogen atoms. All right? And he knew it was neutral. And so he reasoned that what must be happening is that something has to be coming off of this hydrogen atom to make it a positively charged particle. Okay? So he said, okay, this is going to be H plus. But then, because this was neutral to begin with, whatever came off of the hydrogen has to be that negatively charged particle so that when they come together, they're neutral because, hey, a hydrogen atom was neutral. All right? And of course, ultimately, that negatively charged particle was called an electron. But the key point is that he said, well, it must be then, if when these two particles come together, you're going to have a neutral particle, it must be that the absolute magnitude of the charge on that negatively charged particle, the electron, well, that has to equal the magnitude of the charge on that positively charged particle, this hydrogen plus ion. All right, that was the conjecture. Well, if that's the case, if I then take a ratio of delta x minus to delta x plus, right? Delta x minus to delta x plus, what I'm going to get here is just that it will be equal to the mass of the hydrogen ion divided by the mass of this negatively charged particle, the electron. But the observation here is that this deflection for the negatively charged particle is much larger than it was for the positively charged particle. So that must mean, if this is an equality, that must mean here that the mass of this hydrogen ion is much, much greater than the mass of this negatively charged particle, the electron. And this is the stunning result. It's stunning because at the time it was already known that a hydrogen atom is the least massive atom. There wasn't evidence for any other atom less massive than a hydrogen atom. And so here in this experiment, what we're finding is that there is a particle that is less massive than the hydrogen atom. Hey, you can chop the hydrogen atom up. The atom is not the most basic constituent of matter. There is some other particle here, which we're going to call an electron, that is less massive than the hydrogen atom. And that was the first piece of evidence for being able to split that hydrogen atom, or the atom up into smaller particles. The first evidence that the atom was not the most basic constituent of matter. Now, it took another 10 years, Millikan oil drop experiment, for this ratio to actually be measured accurately, and for the mass of the electron to actually be measured accurately. And what we now know is that it takes 1,836 masses of the electron to equal the mass of a hydrogen atom. Okay? Okay.